Now go to the application of how you use Laplace transform to do to solve uh, differential equation, right? The, before we do that, we want to derive the formula that when you solve the you solve differential equation. In many cases, you have a derivative of a function. You want to have the formula for taking a Laplace transform of derivatives, right? Uh, this you have a function f as a function of t, but you take ddt of this one, which is in the text indicated by a pi. Pi is just ddt, df dt. Right? Okay, so we just do it, and we consider that one derivative first, and then generalize that to any number of derivatives. Yeah, that is just plug in the formula. This is t df dt dt, right? And now you just do it as integration by parts, right? That would be f e minus e infinity, and then the second term is f, the integration of f, and then take a derivative of this one, and take a derivative of this one with power minus s, right? And so minus minus should give you a plus sign s, and integrate 0 infinity minus s t. So this one is just a past transform of f. Now the first term is the upper limit is 0 because we have the exponential function. At infinity is 0. So at the lower limit, this is 1, so it's minus f. And then plus s to the path transform. Okay, so this is the formula. The path transform of df dt is the s times Laplace transform f, and this minus the function at 0, that is the initial value of f. Okay, so that's this formula. Is that okay? This derivation is straightforward. Now the next one is second derivative. Pi. Now you just apply the formula repeatedly, right? So it's just copying this form because this is like a Laplacian of f prime prime, right? So you just apply the formula repeatedly. So you just copy, and the first term is this is f prime is 0. You just change f to f prime because now f prime is your function that you want to do Laplace transform. And then the second one is s, Laplace transform of f prime, which is exactly this one. So you can write it down minus f prime 0 and plus s times f0 minus f0 minus f at 0 and then plus s, Laplace transform. It's 2 more minus 1. Yeah, is that okay? So you want to write it back to get rid of this curly bracket and write it back minus f prime 0 minus s f s squared. Okay, and obviously you can keep doing it and get uh, any number of derivatives of f. You get a formula like that, and the final formula, just by guessing the pattern, you probably can guess that the past transform of f, capital F, to the n derivative would be so you actually, I mean, it depends on how you want to memorize it. If you keep the positive term first, the positive term is s to the power of the order of the derivative, so s. The second derivative is s squared, right? First derivative is s1, right? Obviously, the s to the power of n derivative should be the first term, and then multiplied by the Laplace transform f. And then all other terms as just minus term because let's say this is minus, this is minus, minus, minus. Okay, so you can now basically reversing the order. This is Sn term. Another way to memorize it, you should realize now that S has the dimension. If T is if treating T as time, obviously S has the dimension of inverse time or frequency because this S times T is in the argument of the exponential function. So S must have the dimension inverse time. So it's like a frequency. And now just compare this one. So you have take an n derivative means you're taking you have t to the n power in the denominator. So in order to get dimensionally correct, you multiply by s to the n power so that these two are dimensionally correct. It's okay here. So that's one way to fix this n. So it's not any arbitrary power. Must be Sn in order that these two be to be the same dimension, right? And now you write down the next orders would be all the others are negative. So minus s minus one, and now the say it again.
Summation because there will be multiple.
Yeah, I'm just trying to. It's a summation. Just try to write down guess the answer first, right? The next order should be f itself. So the f itself at 0 because now here consider the dimension again. This is n derivative, which we keep n, but you have the function itself, but the Laplace transform take ddt. So whether because Laplace transform is whatever the function multiplied by t, right? So you basically get rid of one time dimension in the denominator. So reduce it s to the n, s minus 1 multiplied by n to get it to be dimensionally correct. Okay. And now you can keep going. So n minus 2 f times 0 and minus that. And finally, it would be minus, the last one would be f to the n minus 1. Let's see. Right? It's like that. The last one is f pi with the second derivative in Laplace transform. The last one is f pi. So if you have taken Laplace transform f to the n derivative, the last one is n minus 1. Okay, so that would be the formula. At least you guess it, and you can show that. Probably can show that by whatever induction method or something like that. You probably can show that, right? Yeah, that's the last equation. 20.1 for the it's okay. So you can actually show that you just guess. The last equation is right. Yeah, it's okay. So let's how much time? Still at 15 minutes. Okay, the next example is it's like a differential equation, not actually like a differential. I mean, this is a little bit strange, but once you know this property, say you just apply it to you can apply it to solve for Laplace transform without actually solving the integral. that. But I mean, provided you know how to take the derivative, so yeah, this is d squared. I mean, the text way the other way around, but it's just the same. It's equation because you know how to take the derivative of sine, right? So second derivative will give you this one. Is quite obviously, right? And now you apply the Laplace transform. So basically, on both sides, minus a squared Laplace transform of sine. Now this is a second derivative, right? So the first one is what do you get? S squared plus kt, right? And subtract the s at f, which is this at 0, right? F is 0, which is this is your f, right? F0 is f0. So this is your f. F0 is t0, so this is 0. And then minus s squared. Oh, no, minus 0, no s. Minus f prime 0. And f prime is f prime is cosine kt times k, right? So f prime 0 is k. So this is k, right? So now you have an equation for the Laplace transform. Just solve this. Combining this two become s squared plus k squared, and this is minus k stuff, and this k divided by s squared plus k squared. Right. This should be the Laplace transform. So instead of doing integration, which is straightforward, you can actually solve it this way. This is not exactly a differential equation. Applying the formula. It's okay. This is like a trivial example. This next one is also slightly less trivial, but because you know how to solve this differential equation anyway, but just to use the Laplace transform method to solve it. This is a simple harmonic oscillator. This capital X. This X. Yes, equals to 0. So this is an initial value problem. So you have the initial value x0 is x sub 0. Then it's times 0 is 3. Okay. And obviously, this is a simple harmonic. So you can actually write it down, the solution, general solution, and plug in the initial condition and get your solution that way. That's not difficult. This is so this illustration how you use Laplace transform. Okay, we do a Laplace transform for both terms. The first term now you apply the formula Laplace transform of this. You have s squared and Laplace transform of x, right? And then minus s times x0, and then minus x minus 0. So that's the first term, right? And then the second term is this k Laplace transform of x. And now substitute these two in the here, these two. So this is 0. This is x sub 0. And then solve for the Laplace transform. So Laplace transform of x will be just putting everything together. Group these two. But this is because the right hand side is 0. We put this term to the other side. We have S, ms x sub 0. That's the right-hand side, and then divided by ms squared plus k. Is that k or k squared? Did I write, did I write down? Okay. It's just k. It's just k. Okay. Well, whatever. It is k. Yes, but you assume k is positive. But this is a spring constant, so k is assumed to be positive. Okay. So that's the Laplace transform, right? Did I get everything correct? It's x sub 0 s squared k. Yeah. And now the solution x should be the inverse transform. Now you just need to look it up. The inverse transform of this one. So I'll give it the right place. So look up the table, right? And yeah, the denominator s squared plus something that is positive. Like in the table, s squared plus k squared, and the numerator as s. So that's look right number 8, right? So this just need to write it like the form of that. You can cancel the m actually, or divide the m, divided by m, just become k by m, right? So the only arbitrary constant x0 in front, and now the rest is the form of item number 8. So this will take the k square. This will take like the k square in the entry. So this is cosine of square of k times 2. Right. That's the answer. So, let's see. Yeah, that's the answer. Okay, so, okay, another simple example. 5 minutes. There will be some a little later. There will be a little bit more sophisticated example that will take a little more time. Maybe just keep doing. What example should we do? The next example is almost like the same, right? This precession of the Earth. Well, it's also oscillation. It's like a simple harmonic oscillator anyway. Maybe doing the impulse. 20, because I mean, the next example, 28 points, you can put that in exactly the same form as this one, so you already know how to solve that by Laplace transform. The next one is a little different. The right-hand side is not 0, so you have the inhomogeneous term, right? So it's still the second derivative. So this is the acceleration times this is the force. Force is equals to p times a constant. At p times a delta function. So basically, at t equals 0, you have just okay, and now you just solve by taking a Laplace transform on both sides. So it's m s squared Laplace transform x minus s x0, and then minus x prime 0. So you need the initial condition x0, x prime, so which where do you give it? both are zero. I think your textbook set both are zero. Set both are zero. And the right hand side is the Laplace transform delta function, which we did that before. It's the exponential function, right? E to the minus s. T0, which is just one now. Laplace transform is just one, so it's just Laplace transform delta function according to your textbook 21. This is 20.140. That is the Laplace transform of that delta function is just one. Okay, so it means Laplace transform x is just p over ms square. Okay, now the x will be the inverse transform of something with a s square in the denominator. So we can now have to look at that. We have to table. Table. Where's this item? S to the power n. S square is especially s square. Right. Item number 3. Right. Item number 3 is the Laplace transform of 2n s gamma n 1 over s n plus 1. Right. And therefore, sorry, right, I got it wrong. So it's this is n square, right? So 1 should be 1. Yeah. 1 will be, n is 1. So 1 and 1 is so it's 1 factorial is 1. You can have that, you can have this one. It's p over mt. Yeah. I meant to check my answer before I write it down. Yeah, that's what I did. Right, so you just need to look careful when applying for formula. Just remember that what is you need to compare the form exactly. Okay, so that is the answer. Anything else? Oh, but this I was answering this question already. This is when you have multiplied by t instead of using gamma function, you can do the inverse. You can do just the transformation in the integration by t, right? That is just doing integration by parts. So you have this one. This one is the integral of this one, right? So e to the minus s e over minus s, and then multiply by t, infinity, and minus of that, minus plus, yes. And one of the s integrations into minus s t dt. Yeah, and that you only know that's one of s, right? And this limit at infinity is 0. And 0 is also 0 because of t. That's 0. This is s. Right? So so you don't like gamma function for integer n, you can just keep doing it, keep doing integration by part and get your formula. So changing gamma function, this is just n factorial. This is n factorial for integer n. Okay.